In this video, we're going to talk about 1.3 Objective 4, where we solve applications involving trigonometric functions. I'm going to be using my calculator for most of this, but I also have a whiteboard over here just to show you some steps on some of these. So let's go ahead and get started here. A projectile is launched from the ground at an angle of theta above the horizon with an initial speed v in feet per second. Its range, which is the total distance traveled by the projectile over level ground of the projectile, is approximated by the equation x equals v squared over 32 times sine of 2 theta. Find the launch angle of the projectile with an initial speed of 90 feet per second. So I'm going to stick 90 in for the v here. 90 squared divided by, let me put this in parentheses here. Divided by 32, sine of 2 theta, like that. And I want this to be equal to 170. And we'll put 170 here. Mode, I'm in degree mode. Window, I'm going to go between 0 and 90 degrees by 15 degrees. Because I want my launch angle to be somewhere between horizontal and vertical. And I'm going to guess that my maximum range here is going to be less than 1,000 feet, but I don't know that for sure. There we go. And so I've got 2 points of intersection here, second calc number 5. First one is at about 21 degrees. They tell me to round to the nearest degree here. And the second one is about 68 degrees. And that makes sense because that's 21 degrees off of 90 degrees. All right. Same equation. Now we're going to be in radian mode for this one. And we want to be less than 540 feet. So let me change my window here. So this is 0 to pi over 2 now. And we're going to make this pi over 8. And our initial launch, this is going to be 160. That. There we go. And so we want to be between 0 and this first point of intersection. And then this last one is going to be pi over 2. Rounded to 2 decimal places is 1.57. Our graph now, second calc number 5. Right about there, 0.37. And second calc number 5. Is 1.20. All right. This next one, I'll use the whiteboard a little bit just to help you see what I'm doing. That the circumference of the Earth is also the circumference of my first rope here, is 24,882 miles. I need to change that into feet, though, by multiplying by the conversion factor, 5280 feet in 1 mile. I believe that's the conversion factor. So upside down. 1 mile is 5,280 feet. So pull the calculator over here for a second. 24,882, 5,280 feet. All right, and then we'll want to figure out the distance between the center of the Earth and this rope here. So that's 2 pi r. Divide both sides by 2 pi. Zero 90929 2.59. Okay. And then we're going to have another rope that is 44 feet longer. So that's why I converted things to feet here. So I need this answer that's in feet plus 44. So C2 is 13,77,004. I need to divide that by 2 pi to get its distance from the center of the Earth. R2 equals 20909,299.6. I want this number minus that number to get my distance in feet. So R2 minus R1 equals 7.01 feet. And we're told to give our answer to the nearest foot, which is 7. This model here is one that we're going to use a lot in differential equations. It's a cosine of omega t, where a is my amplitude and omega is equal to 2 pi divided by what would, or period is equal to 2 pi over omega. Let's do that. I guess that's the way to write it here. So we're going to solve for a and omega and plug it into the formula here. Really, they tell me my amplitude. They tell me that I stretched at 6, and to assume that that's the amplitude, so 6 centimeters there. Nothing to solve for, but our period we were told was 10 seconds. It's equal to 2 pi over omega. So omega equals 2 pi over 10 is equal to pi over 5. So we have pi over 5t. That's it for this video, and we'll come back next time and talk about 1.3, objective 5. See you for the next video.